SVA is a very expressive and concise language. In just a few characters you can describe some really complicated behaviour, so complicated in fact that it's hard to understand what it actually does. So the question asked here, maybe I should open a competition or something, but we're going to go through some example and hopefully you'll agree that in a very few characters you can rapidly describe something which is almost impossible to understand without a lot of thought. And surely if you're going to sign off your design with these properties you're going to be rather concerned. So let's take a look at an example. This isn't the actual property we're going to talk about. This we're just working up to it, just to show you how things go from trivial to hard to understand. So this is my desired circuit here. You can see the schematic here with an OR gate, and what the assertion says is if B is true, then on the next cycle then C should be true. So as this is an OR gate, then obviously it doesn't matter what A is doing. This is going to be true, and it's fairly easy to see that. Okay, so that's an example of something that's really easy. And if we had an incorrect implementation, like we chose the wrong gate, for example, we chose an AND gate instead, now it doesn't matter what A is doing, of course, because if A is always 0, then the output's always 0. The output C is always 0. So this property will detect that incorrect implementation. So far, so good. However, this is the property we're talking about here. This is relatively few characters, and I could already see an optimization here. Instead of saying 1 tick B1, I could have just put the number 1. Okay, so I've got to save myself 3 characters already. So the question being asked is, given this assumption, will this property shown here detect this incorrect implementation? So I've already determined that yes it would without the assumption considered, but with the assumption would it or would it not? With a constraint and the incorrect implementation, the property status for this property here will be pass. So remember, assertions pass under 2 conditions: if we have B followed by C in the next cycle, or if B never occurs. So let's take a look at what this property says. Okay, so what it's saying is if we have not C followed the next cycle by 1, which is true, repeated, this plus means 1 to an infinite number of cycles. So if we have not C, and then this will be true forever afterwards, this implies that the same cycle, so the cycle after C, A will be true, and all subsequent cycles, because this property gets enabled every single future cycle after we've had not C being true. Okay, so I told you it was rather hard to understand. So what effect does this have then? Well, it all depends on this assertion passing on what the initial value of B is. Okay, so what the reset value of B is, or however else we initialize the design. So if we initialize the design with B being a 0, then what this means is that is not C is true on the first cycle. So after the first cycle, A will always be true, meaning this property is always going to be true then. However, if B is not true on the first cycle, then A will not be true, will not be required to be true until the first time we observe C being 0. So I said that was complicated. So the bottom line here is that going from a simple circuit that we knew this assertion would detect a failure, the assumption hides that from us, and all of the kind of normal metrics we use, like the status of the property, whether the left-hand side of the property can occur or not, and whether A, B, and C can all take on value 0 or 1, this assumption hides that problem. So how do we know we did something wrong? Well, that's the million-dollar question, of course. So just to show you, this isn't a lie. This is the result in the tool here. We can see, and strangely enough, if the reset value of the flip-flop is a 0, then the assumption masks the error. If the Jasper can choose, i.e. there is no initial value for that flip-flop, then we do detect the error. Okay, so just in that many characters, so remember we could optimize this by deleting these 3 characters shown there. In that few number of characters, we've created a really hard to understand situation on this design which only has 1 flip-flop and 1 gate and a simple property. It's made it really difficult to be even 90% confident you understand what's happening. Please feel free to send me any other examples you have. If you can create something that's hard to understand in fewer characters than this, I'm sure it's possible. And of course, it's always subjective, how hard it is to understand or not, of course. But hopefully this demonstrated to you. Think very carefully about when writing SVA properties. Just because there's a small number of characters does not mean it's easy to understand. That was the point of this video. Okay. So thanks for listening, and I hope you found it useful, and goodbye.